Okay, we'll start. Okay, so we are looking at the MATLAB toolbox for optimization. So last class we looked at the introduction to toolbox and also how to do the linear programming problem. So this class we look at how to do the single variable unconstrained optimization. Okay, so what is the subroutine for that? Okay, so this subroutine is based on the golden section method and it can take only one variable x. Okay, so this is the format of the subroutine. That is f minimum boundaries. Boundaries means you have to give the x1, that's the lower bound, and x2 is the upper bound of the x variable. Okay, and then fun is the definition of the objective function. And the options is something you have to set before you call the subroutine. Okay, so um, there are different ways in which you can write the objective function. Okay, so either you can open a file called fun.m and separately type in your objective function. So that is necessary for very big objective functions. So then you need to open a separate file called fun.m and type the function. Okay, and another option is you can define the objective function in a single line like this in the main calling program itself. So if you write it in the separate file called fun.m, then here you have to type fun in apostrophes. Okay, you have to put fun in apostrophes. So that means it is being taken from fun.m. That is from a file. So if it is, if the function is a one-line function in the main code itself, you don't need this apostrophe. Okay, so let us look at an objective function like this. So how to minimize? F is equal to minus 2x minus x squared by 20. So this you can write in a single line like this. Okay, and x1, x2 are the variable bounds. So that is the lower and upper values of the search range. Then before you use this function, you have to use this options equal to optim set f minimum boundaries. So that will load all the default values of the subroutine. And if you want to change some of the default values by yourself, then you can individually give the parameters like this. Tolerance of x is equal to 10 raised to minus 3, maximum number of iterations equal to 100, etc. So you have to look up in the help file. So if you type help f minimum boundaries, you can MATLAB will tell all the details of how to use the subroutine. Okay, so we are going to see the example of how to do the minimization of f is equal to minus 2 sin x minus x squared by 20. So this is how you do that. So first options are set like this. Okay, so just as an example for this particular problem, I am manually setting the options. So this is not required if you accept the default settings. Then x1 equal to 0, x2 equal to 4. Or in other words, the search range is from 0 to 4. So then I define the objective function in one line. The fun is equal to at x of this thing. So this is the objective function. Okay, so when you supply the value of x in this objective function, it will return this value, this entire value. So that is how this function works. Okay, so now you call this subroutine by this statement. Okay, so this you can see FU1, the objective function definition is here. Okay, so now after this line is executed, the values of the x, that values of the design variable x will be shown here. Okay, so this is the correct value of x where the optima, of course, and the f1 is the objective function value. So that is minus 2.13. So this is done with the golden section method. So next we look at multivariable unconstrained optimization. So this is like our.
Sir, one question, sir. I'm sorry to ask.
No?
Sir, one question, sir. If you want to plot that graph, suppose this function graph.
That in the MATLAB some plot command is there. Like you have to plot f file. Okay, you can use this plot command like this. Plot f file x. Okay, then it will plot.
Right. Thank you.
So this is only one value. Okay, this is only one value. So you want to plot this objective function.
Exactly,
Okay.
sir.
Okay. For that, what you have to do is that you have to define x as an array. Okay, x is from 0 to 4 in steps of 0.1. Okay. So okay, so this is the x-axis. It will store all these values in this x array. Okay, then you type fun of x. Okay, then fun of x will x will generate an array that is corresponding to each value of x. It will calculate the f values. So after that, you can put plot fun x. Okay, so then it will plot the objective function for all these values of x. Okay, so this means x is starting from 0 to 4 in intervals of 0.1. So that's the meaning of this. And when you substitute it here, you will get all the matching values of the objective function. So as I told earlier in MATLAB, each variable x is actually an array. So you can define x as an array and substitute it here. And then if you type fun, you will get all the corresponding values of fun of x. And then you can do the plot. Okay, so you can check the plot command in MATLAB.
Thank you, sir.
Okay. Missed call, Walker. Okay, so we'll go to next. So multivariable unconstrained optimizer. So this is like your Cauchy's method, Newton's method, Fletcher-Reeve methods, etc. Because this will do that same thing. Okay, so that is how to find the minima of multiple variables. Okay, so two subroutines are there which will do the job. So this f minimum unconstrained. Okay, it will use the gradient method or calculus based method. So this, I think this uses the Newton's method, which we studied already. Then f minimum search. So this uses the random search algorithm or the grid search. Okay, grid search, as we know, will divide the domain like this, and it will, search like this. It will search like this. So, so this f minimum search will not use any calculus based method. Okay, it will only do the grid search method. So we will try the efficacy of both. Okay, so first we look at this f minimum unconstrained. So this is the format of the f minimum unconstrained. Okay, so one is the definition of the objective function. X naught is the what is it, the vector of initial values of x. Okay, suppose x, y, z is there. So a vector of initial values is 1, 0, 0, or a starting point is 1, 0, 0. That is given in this vector x naught. So I don't see the search range in this. Probably there is an option for search range, but it is not shown in this example. Okay. So you can type help f minimum unconstrained. So that will show you all the options with this function. Okay. Okay, then as usual, before you call the subroutine, you have to set the options to the default values. That is f minimum unconstrained. So we'll do an example. So we'll minimize this objective function, which is based on two variables, x1 and x2. Okay, and it is not convex. Okay, so it will have many local minima. Okay, so we'll see how this affects the algorithm. So it has many local minima, and one of the local minima occurs at xy equal to 0.5 minus 1, and that value is equal to 0. So if you look at the contours of this objective function, it will have many local minima. Okay? So we want to find the local minima at the 0.5 minus 1. Okay, and this f value is 0. F is equal to 0 here. So other local minimas are there, but let us see if we can correctly identify this local minimum, okay, by giving this starting point close to this. Okay, so we will try two initial values, 10, 10 and 1, 1. And we will see if it converges to this local minimum. So 10, 10 is very far away. Okay, 10, 10 is very far away. Okay, so we'll try both. Okay, so this is how you run this code. So first you set options equal to optim set f minimum unconstrained. So this will set all the default options for this algorithm, like tolerance, number of iterations, etc. So the default values, if you want to know, you have to type the help command and see. Okay, and starting point is the x naught, that is 10, 10. After that, you define this objective function in this line, in a single line. Okay. Then you call this subroutine to find the minimum. So the x value will be stored in x, and objective function value will be stored in f1. So let us see the results. So we are getting the solution as x is equal to minus 2 and 8, and the objective function value is 40. So this is not, it is not our local minima. Okay, our local minima is at another place. Okay. Our local minima is minus at 0.5 minus 1. Okay. Okay, so let us try another starting point, 1, 1, because 1, 1 is close to 0.5 minus 1. Okay. So now, after I give 1, 1, and after I call this objective function, now I am getting the correct local minimum. That is 0.5 minus 1, and f value is 10 raised to minus 12 is equal to 0. Okay, so you can see that if the objective function has many local minima, then you have to give the starting point close to that particular local minima. Only then the algorithm will go there. Otherwise, it will go somewhere else to some other local minimum. Okay, so up to now we did not see the detailed output of the program. We only saw the x value and the value of the objective function. So we can use this output option in the subroutine to see more useful data. So what you do is that, okay, this is the same thing in the last slide. Only thing is that I am adding two more output parameters. So I have added one exit flag and an output. Okay. Okay. So now after the program is run, you will get the value of exit flag and you will get the value of output. Okay, so the exit flag is actually an integer. In this case, it is 1. So the meaning of the exit flag is given in the help command. So each integer has a particular meaning. So exit flag 1 may mean that the function has converged properly and the answer is correct. And the exit flag 0 may mean that some error has occurred, like divide by 0, or it has gone into some negative region. Okay, and the exit flag 2 may mean that it did not converge properly, but some sort of convergence is there. So the meaning of the exit flag integer has to be checked with the help command for that particular subroutine, and you can understand whether the solution is correctly converged or not. Okay, then another thing is that, okay, some output data has come. So if you type output and press return, so it will show all this data. So it means that 17 iterations of the algorithm has taken place, and objective function was called 57 times. That is to evaluate the objective function value. And algorithm is medium scale quasi-Newton method. Quasi-Newton method means that modified Newton method, which we already studied. It is same as the modified Newton method, where we do the line search along the objective function. Okay. So if you want to have further extra data like this, then output option has to be enabled. Okay, so next we go to this function f minimum search, so which is based on a random search method or a grid search method. So we already studied the grid search method. So you have to define a grid of size delta, and then the user gives starting point, and it will go from one grid point to another grid point, checking where the minima occurs. Okay. So this is the format. So f minimum search. Okay, this is the definition of objective function. It's the starting value. These are the options like number of iterations, tolerance, etc. So let us repeat this the previous objective function with this f minimum search, which is based on grid search method. The previous method was based on that modified Newton's method. Okay, so the same example is done with the random search. Okay, so options are set here. So you try first x not equal to 1, 1, and you define the objective function. Xf function value is equal to, this is the call of the objective function. So now you can see that it has found a minima which is very far away from where we started. So we started at 1, 1, and it has found a minima at x equal to minus 763 and y is equal to 120. And the objective function value is 0 there, but it has gone to a totally different unexpected place. So this is not what we are expecting. Okay. Okay, so now what we do is that we will guess with we will give a guess which is very close to 0.5 minus 1. So we will give 1 minus 2. So 1 is very close to 0.5. Minus 2 is very close to minus 1. Okay, so after we give this x naught, which is very close to our local minima, then it is able to converge to the local minima which we want. Okay, so in this example, the direct search algorithm performance is inferior to the gradient based example. The gradient based algorithm worked better than this method. Okay, so this random search algorithm may perform better than the gradient based if there are large number of variables. Okay, so it's in certain circumstances, this direct search algorithm may be better than the calculus based method. Okay, and also some experimental data which is captured with the help of sensors and all. So those curves may be very sharp like this. So they cannot be solved with the gradient based method. Okay, because when you try to differentiate the sharp peaks, error will occur. So for this type of rough curves, you have to use the direct search algorithm. Okay, so for certain circumstances, this direct search algorithm will work better than gradient based algorithm. Okay, quadratic programming we have yet to start. So temporarily we can stop this optimization toolbox. I will now give the assignment. Okay, next assignment I will give with questions up to the Fletcher-Reeve method and having both MATLAB and hand calculations. Okay, so let us stop this thing. Okay, we can start the next topic, that is the constraint optimization. Okay? Constraint optimization method. We can start a little bit and then stop. Okay, so next we look at the introduction of how to deal with optimization problems which have constraint equations. Up to now in this Fletcher-Reeve method and Cauchy's method and all that, we only considered the objective function. We didn't consider any constraint equations. So when constraint equation comes, then it will become much more difficult. Okay, so constraint optimization methods, how to deal with constraints. So two different methods are there, analytical and numerical. Yeah. Analytical method means you have to do by hand. You have to do the differentiation and first derivative, second derivative, etc. You have to do by hand. And the favorite approach is called Lagrange multiplier method. So we study this Lagrange multiplier method for some simple cases. Okay, like two variables. Okay, so so this Lagrange multiplier method can be used for equality and inequality constraints, and it allows us to check for active and inactive constraints. So as I told you in the earlier lecture, a constraint can be active or inactive. If a constraint is inactive, you can simply neglect it and just find the global minimum. And if a constraint is active, then you just solve for the intersection of the equation of the constraint and the objective function. Okay. So the boundary, so the solution will lie on the boundary of the constraint. Okay. So we are going to study some methods to check if a constraint is active or inactive. Okay. Then this is suitable only for simple problems. Actually, nobody uses the Lagrange multiplier method to solve optimization problems because it is too difficult. So everybody now use only numerical method. So this numerical method we'll study later. Okay. So we'll just look at some introduction. The method of Lagrange multiplier for equality constraints. So first we will study Lagrange multiplier for equality constraints. After that, we will extend it to inequality constraint. So what are the special features of optimization problems with equality constraint? So equality constraints are always active and the optima will always lie on the constraint, always lie on the equality constraint. Okay. Then previously we studied some method of solving equality constraints by eliminating one variable from one constraint equation, but that is not always possible. It depends on how the constraint equation is written. Okay, in certain type of constraint equation, it is very easy to separate the variables. You can bring x to one side and then y and z on the other side, and you can express x as a function of y and z. But in some equations, the variables are all mixed up and you can't separate a particular variable. So Lagrange multiplier method is more fundamental and it can be used in such circumstances. So we'll just look at one example where our normal method fails. Okay, so dealing with equality constraints. So in the earlier class, we looked at this problem. So minimize this objective function subject to this equality constraint. So in this equality constraint, we took z to one side and xy to another side. So 3xy plus 2z into 4x plus 4y is equal to 100. Okay. Okay. So z is written in terms of x and y. Okay. So z what is that? 100 minus 3xy by 2 the 4x plus 4y is equal to z. Okay. So in this particular example, we are able to write z in terms of x and y. So for this particular example, but that will not always happen. So now in this same problem, I change this equality constraint. Okay. So now all the variables are mixed up. Can you take z out separately or x or y? It is not possible. Okay, z into x squared plus y z minus x by y is equal to 1. So you can see that z is occurring inside this thing. So you can't separate z out. Yeah. So because of this situation, so in this constraint, it is impossible to separate out one variable in terms of the other variables. Hence, we cannot modify the objective function in these cases. So we need a general method to solve the equality constraints. So that is where this Lagrange method comes. A Lagrange method comes. So I think we can stop here because once I start Lagrange method, then it will not stop in 5 or 10 minutes. So we can stop this lecture now. Okay. So I'll send the assignment to you in a few days. Okay. I have to take the attendance. So I stop recording.